Alright. This lecture is going to examine the Fourier series. Fourier series. Alright. So first let's get a little bit of terminology. So we have the period, the fundamental period, which is T naught, capital T naught. Fundamental frequency, which can be expressed in one of two ways. F of naught is equal to 1 over T naught. And then we can also say that this is omega naught is equal to 2 pi divided by T naught. So frequency is in hertz, omega is in rad per second. So a periodic signal can be expressed in terms of a summation from k is equal to negative infinity to infinity of a of k, lowercase a of k, e to the j omega naught kt. So any signal can be represented as a sum of sinusoids. And as we saw last lecture with the Euler's formulas, this is just a sinusoid. This is that corkscrew spinning through space. And so it's a complex sinusoid. If we sum these from all values, k is negative infinity to infinity, with some scaling factor out front, we can create anything. Alright, we can rewrite this to say this is also equal to the sum from k is equal to negative infinity to infinity of a of k, e to the j, 2 pi over T naught k of t. So this is bringing in this fundamental frequency into the equation. Alright, the big question, how do we find the AKs? These are the constant values that scale the function. How do we figure out what the magnitude is for each value? Alright. There are two ways to do that. How do we find the AKs? Two ways. The first way is analysis. And this can be directly expanding Euler's formula. So we can directly expand this and do math. So directly expand Euler's. And remember, so yeah, I'm not going to go through the math. You can do that. We can expand out basically any equation and write it as a sum of the e to the j omegas. Alright, the second way to do it is via integration. Let me see if you can still see this on the video screen. Yes, good. Alright, so this is the method that we usually use in lecture or in class. A of k is equal to 1 over T naught, the integral from 0 to T naught of x of t e to the minus j 2 pi divided by T naught kt dt. And let me write one more thing. This is any periodic signal. So any periodic signal can be expressed as a sum of these, where it's centered around this fundamental frequency. Alright, so this is where A comes from. So we can integrate over any period. So we can slide this around. We don't always have to go from 0 to t naught. We could go from negative t naught divided by 2 up to t naught divided by 2. We could integrate over any period. We just have to capture one cycle of this periodic signal in order to get the energy that is in the given fundamental described by K. Alright. Sometimes it's tricky to find K is equal to 0. Then it's often better to directly evaluate at K is equal to 0. So we can substitute in for omega is equal to 0, and that gets us, this board is small, so I'm going to have to erase a lot. So we can directly evaluate A of 0. So A of 0 is equal to 1 divided by t naught, the integral from 0 to t naught, and again we can shift that around. X of t dt for omega is equal to 0. So what does this mean? So it means if x of t was equal to sine omega t, we put in 0 for the omega, and then we solve out that integral. This is finding the DC power that is involved in this signal. So really what we're trying to do is see the initial energy that's in the system at omega is equal to 0. Alright, we have some very special properties. Let's just start off with this one. So, if x of t is real, so these are properties. So, if x of t is real, then a of k is equal to a of negative k complex conjugate. Okay, so symmetric with a complex conjugate. Okay. If we expand this now, so you've already seen Fourier Series in your previous courses. Now the question on this one is systems and signals. So if this is the signal, so I guess the way I wrote these notes up, we just introduced this one. We'll introduce some more properties a little later. So how does this fit in with an LTI system? So LTI systems. So if x of t is the input to the system, y of t is the output, then what we need to show is that y of t is equal to the summation from k is equal to negative infinity to infinity of a of k times h of j omega naught k times e to the j omega naught j omega naught kt. This is an expansion upon the convolution integral that's combining it with the Fourier series. Alright, so now let's look at this. If x of t is real, then we can do this substitution. So, if x of t is real, then we can say that y of t is going to be equal to a naught plus the summation from k is equal to 1 to infinity of a of k, h of j omega naught k, e to the j omega naught k, plus the summation from k is equal to 1 up to infinity of a to the negative k, that's doing this substitution into here, h of negative j, there's where that conjugate comes in, of omega naught k, e to the j omega naught k. Alright, so what we did, we took the original equation, we pulled out the DC because it's real, so that term is not going to have a complex conjugate on either side. It's the 0. Then for each positive value from k to 1 to infinity, we left it as is. But now, instead of doing the negative values, we know that we can go again from k is equal to 1 to infinity, but we're going to put in a negative k, and we're going to put in the complex conjugate into the transfer function. So this is going to find the output working directly off the transfer function with that complex conjugate property. Alright, so we can simplify this. You can see that these summations are over the same region, so the general intent is to move this through and get an equation that solves it, only doing one summation. So, a of 0 plus the summation from k is equal to 1 up to infinity of all of the stuff that's going to follow. This is supposed to be a square in the bracket. I'm going to use a parenthesis instead. Of a of k, h of j omega naught k, e to the j omega naught k, plus a of k conjugate, h of conjugate of j omega naught k, e to the negative j omega naught k in summation. Alright, so we pulled some things out, used some properties to transform the negative signs and move those around so that we can put these in terms of similar a of k's. So we got rid of the negative. I'm going to leave that down here so we can see the next step. Alright, going back to the top of the board. We're going to keep this a of 0 out front. I'm going to move to the right just a bit so I have a little more room. A of 0 plus the summation from k is equal to 1 up to infinity of all of this stuff. Now if we look at this, we have this guy, and this guy, and this guy, and this guy, and the only thing different from them are the complex conjugate of it, but this is the positive and this is the negative. So this is the form of a complex number that we can pull out this value and this value, except we know they're going to be different in their complex conjugate nature, but their magnitude's going to be the same. So we can pull out just their magnitude and then take care of the complex conjugate in the phase notation. Alright, so we can take the magnitude of a of k. Because these are the same magnitude, the complex conjugate changes the sign of the angle. Same thing here. Same magnitude, it changes the sign of the angle. So we're going to pull out the magnitude of a of k and the magnitude of h of j omega naught k. And then we're going to end that there. And then we have e to the j omega naught k. There should be a parenthesis right here. Now, this isn't done. I'm going to continue to write here. But what is this? This is the angle So if we're pulling out the magnitude, this that remains is the angle. E has a magnitude of whatever's in front of it, and an angle right here. So because we know this is the complex conjugate, we can take this and put it up into the angle notation. Alright, so this is going to be j of omega naught k at an angle of a of k plus the angle of h of j omega naught k. Alright? So now we can expand that out. And so that takes care of this one, is looking at this first term. So it's got the positive j omega naught k, and then we added these two angles to it. And there should be a plus sign right here. I'm missing. Sorry. So this should be plus the angle of a of k. We're adding the angle because this does not have the complex conjugate. So whatever the angle is here, we're just maintaining that, but we're moving it up into the polar notation. Alright, so now we can add and change this guy into that same notation. So, again, the absolute value of a of k, h of the j omega naught k, and this is going to be multiplied by this. So let me just, I think I'm getting things messed up a little bit as we go along, so let me clarify. This is this. This is this with the angles put up in here. This term is right here. Now we have to write the angle term, the second one. Then we're going to be able to factor these out. E of negative j of omega naught k plus, now I have to take whatever angle was here and move it up into the angle space. So this is, the negative sign has been factored out. So it's going to be angle of a of k plus the angle of h of j omega naught k. Right? If we were to distribute this negative sign through all these, we'd see that this is a negative, this is a negative, this is a negative. That's where this complex conjugate comes from, is flipping the sign in the exponential. Alright. Great. So now we have this big thing. But now we can start simplifying because this and this are like terms, so we can factor that out front. So now we have a of 0 plus the summation from k is equal to 1 up to infinity times a of k, h of j omega naught k, absolute value of that guy, the magnitude. And then that's going to be plus, oh, I should follow my notes. If we look at this, we have an e to the j plus an e to the j. There's an Euler's identity that turns this into 2 cosine of omega naught k plus angle of a of k plus an angle of h to the j omega naught k. Okay, so Euler's identity is e to the j plus e to the minus j is equal to 2 cosine. Okay, so this is the final answer. So we can say that y of t is equal to a of 0, and we can directly evaluate a of 0 to get how much DC content is going to be in the output system. That's going to be plus the summation from k is equal to 1 up to infinity of 2 times that sum. Absolute value A of k h j omega naught k into absolute value times the cosine omega naught k plus the angle of A of k plus the angle of h of j omega naught k. This is for x of t is real. So we use the property of A of k in order to simplify this expression. Now, what we really want to think about here is how does this work? We have these signals that are going into the system, and we now can rewrite the system in terms of h of j omega naught k and the A of k, which describes x of t, and get the output. This works because these are similar to orthogonality of signals. And in orthogonality, when we have a dot product of A dot B is equal to 0, but if they're collinear, A dot C is going to be equal to the max value if they're collinear. So in that same manner, if things in this region are going in the same direction, they'll sum up and all be included in the same sum. So let's examine that just a little bit more. With signal orthogonality. Signal orthogonality. So if we have 1 over t naught, the integral from negative t naught divided by 2 up to t naught divided by 2, so the integral for one period normalized by the period, x of t multiplied by y of t complex conjugate dt. This is like a dot product. This integral is like a dot product. This is like a dot product for periodic x and y signals. Now, we'll explain this more as we go. So for now, I'm just introducing this integral, and we'll explain it more.